Welcome back. So we have yet another example on the concept of this chapter. Let's get right into this. It says the 40-kilogram block shown in figure 2b is moving up initially with a speed of 3.5 meters per second. So this is the 40-kilogram block. Say block A is moving up initially at 3.5 meters per second. What constant value of P? So this is P right here will result in an upward speed of 6 meters per second in 10 seconds. So that means we want the speed of this to go from the 3.5 meters per second it started with to 6 meters per second, and we want that to happen within 10 seconds. That means we want this to be accelerated, and of course if this is going to be accelerated it has to be moved up, and that will only happen through the tension in the cable that connects it to this and also to this end, such that when this force P is applied, it drags this body along, and by that it drags this also, and by that it drags the 40-kilogram body. So we want to find out what value of P will make that happen. That is, what value of P will give this an acceleration such that it goes from 3.5 meters per second to 6 meters per second within 10 seconds. Okay, so that is the work we have to do here. And of course, it says assume that the weightless pulleys, so the pulleys are weightless, light, and frictionless, okay, are frictionless, and that the coefficient of friction between the blocks and the plane is 0.10. So we have coefficient of friction here. Obviously, there is motion in this system, so there is no doubt as to whether the system is in motion or not. So we are not going to find out whether there is motion in the system or not. Okay. And by that, we know if there is any coefficient of friction, it has to be the coefficient of kinetic friction because there is motion between the surfaces in contact here. So what we have been provided with is the coefficient of kinetic friction. Even though that is not stated here, we can tell that it is the coefficient of kinetic friction because there is motion in this system. So let's get right into this. Of course, we will stick with the method or the approach we have taken so far for connected bodies. That is, firstly, get the relationship between the accelerations of this body, then analyze what we have here. And of course, in this case, we have been asked to determine the value of some force P. So that means we should complete some sort of kinematic analysis so that we will obtain the acceleration of the bodies present. We can obtain the acceleration of the bodies present from the kinematics. Then once we obtain the accelerations, then we will do the kinetic analysis to obtain this force P. Unlike other examples, some other examples we've had so far where we wanted to get some kinematic parameters, where because of that, we needed to do a kinetic analysis first, obtain the acceleration from that, then use the acceleration to complete the kinematic analysis. In this case, we have some kinematic parameters provided from which we will obtain the acceleration because first is what's required here, not some kinematic parameters. Okay, so I think that is the approach we've taken so far in general when dealing with kinetics problem. So we will start off by, of course, we will start off by considering the relationship between the accelerations in this system. So let us start off with that. So for the solution to this problem, we will reproduce the diagram as it is so that we can label the accelerations appropriately. So firstly, we want to do a kinematic analysis. Reproduce the diagram as it is. So you can pause the video at your end and just do that first. All right, so this is the diagram provided. So we have labeled these bodies A, B, and C. So we know a body A is the 40-kilogram mass, body B is the 15-kilogram mass, and body C is the 10-kilogram mass. Okay, so what do we make of this now? We need to get the relationship between their accelerations. Yes, 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 yes. We know that they will have the same acceleration. Okay, that is quite clear because if this body is dragged down, okay, that down this incline, we know this will go up the incline, this will go to the left, and this will go down. Okay, and of course it is evident in the problem statement that this will be going up, so we might make use of that information directly and say, okay, we know for this to go up, this has to move this way and this has to move down. And if this is going to move up by 1 meter, it has to be that, because the connection is quite simple here, it has to be that this will move to the left by 1 meter. It has to be that this will also have moved down the incline by 1 meter. So we're very certain that the accelerations will be the same. Okay, however, we are sticking with this method here to avoid any confusion and to avoid introducing any new concepts or any new notes that might complicate what we have been dealing with so far, and to completely avoid confusion when you have problems of this kind. So the approach we have taken so far, which is what I recommend that you take, is applicable to all kinds of problems, including this one. So that is why I want us to take this approach. Okay. So for this situation, of course, we'll identify fixed points and fixed axes in the system from which we can draw the from which we can indicate or determine the position for each of these bodies. Okay, so we can say that if we this is a fixed point in the system, this is a fixed point, this is a fixed point, this is a fixed point. So by that, we can say if we extend some vertical line here, okay, and we extend some vertical line here, so we can say this is some vertical line. Now this choice is arbitrary. I mean, you are horizontal line, please, so you might want to choose something different for yourself, and that will be perfectly fine. So I'm going to extend this line here so that it's perpendicular to this, and then we can have this as the position of body C, and I'm going to call that XC. You can call it YC if you like, and we're going to do this to capture the position of body B. So we can call that XB, and we're going to do this to capture the position of body A, and you can call that XA. So with that, we are good to go. We have now used all of these. I mean, we have extended all of these axes from some fixed points. So these are attached to these fixed points. Okay, and this one is attached to this fixed point. So let's just capture the position of the bodies. So the next thing to do is to write a relationship between the positions of these bodies based on the length of the cables connecting them. Okay, we know that for the dependent motion of these bodies, the cables are inextensible, meaning that the length of the cables are constant. So for the first cable, you can see there is a different cable that connects A and B than what is connecting B and C. So if you consider the cable connecting A and B, we sum up all of its length, then let us say that is some length L1, the length of cable 1. That will be, so we know from here to here is XA. Of course, we know XA has to increase with the or decrease with the position of A changing. So we know it has to be something that is along the position of A. That is why it is vertical. Okay. For B, it has to increase or decrease with the position of B changing. So that is why it is horizontal. And this also, that is why it is along the incline, because it has to increase or decrease with the position of C changing. That is very important to note when dealing with problems of this kind in general, as we've seen in this chapter so far. So for this, we have the length here to be XA, then plus the length here, which is XB. So that is going to be XA plus XB. Okay. Quite straightforward. Of course, you might be wondering what are the lengths here. Now, the point is, as we pointed out in this chapter so far, irrespective of the relative positions of bodies A and B, the length here will be constant. So you might want to include it, you might ignore it. The reason we can ignore it safely is because we will have to differentiate this. And since this portion and the length of this portion is a constant, by the time we're differentiating, the derivative will become zero. So at the end of the day, it has no effect on our overall analysis, because obviously we're not using this to get the positions per se. We're using this to get the relationships between the velocities and accelerations, which will involve derivatives of the length. So any constant length, that is any length over any portion that we know will remain constant over time, okay, we will not have an influence on our overall result at the end of the day. Okay, so that is why we can safely ignore that. And now we know there is another cable here that connects bodies B and C, and so we can call that L2. We know its length is also going to remain constant for the motion of these bodies to be independent. So that will be XC then plus this length, okay, from this point to this point. But we don't know what this length is, okay, from this point to this point. Obviously, that is not XB. However, we know if we're going to get that length, we can do something like this. We know the length from this end, because this is a fixed point, okay, to this other end, which is also fixed, okay. This is a fixed axis here. I'll say this is a fixed point, and you extend it from that point. We know that that length is fixed. So if we call that length X, we know it is a constant. Then we can get the length here. That is going to be, so if you extend this length will be x minus xb, where x is a constant, okay? And then we have this plus xc. So we're going to have x minus xb. So x minus xb is this length, and then plus xc. So this will be plus xc. Of course, there will be some portion here which will remain constant all through the motion in the system. That's what we're interested in now. Okay, so with this we have a relationship between the positions of all of these bodies, and we can differentiate. If we differentiate the first time, we will get the relationship between their velocities, and if we differentiate the second time, we get the relationship between their accelerations. And if we differentiate this, with respect to time, of course, derivative of L1 with respect to time will be 0, because L1 is the constant length, total length of the cable 1, and this will give us VA equal A plus VB, okay? And when we differentiate the second one, the derivative of this gives us 0. Derivative of x gives us 0, because x is a constant. It is a distance between two fixed points. So that is a constant, and that derivative gives us 0. Then we have minus derivative of xb, which is vb, then plus the derivative of xc, which is vc. And differentiating once again with respect to time, we know derivative of velocity with respect to time is acceleration. So this will give us 0 equals, so I want to write that acceleration. So I'll differentiate this. We're going to have acceleration of A, then plus acceleration of B equals 0. And if we differentiate the third one, I mean the second one here, it gives us minus acceleration of B, okay, plus acceleration of C equals 0. Okay, of course, this agrees with the fact that acceleration of A will be equal in magnitude to acceleration of B, and likewise, acceleration of B will be equal in magnitude to the acceleration of C. So that is quite easy to see from here. But of course, these are algebraic relations which will have the same impact here as vector relations, because they help us capture the relationship between the algebraic values or the vector values, so to speak, of each of these accelerations. So it tells us that when AA is positive, for instance, AB is going to be negative, and vice versa. So if AB is negative, this will be positive. If AB is positive, AA will be negative. And that means that if, look at it now, if AA is positive, so the positive direction for AA will be when this moves down. So that tells us that when this moves down, okay, this will be AA will be negative, which means A will be AB will be negative, which means B will be going in the negative in its own negative direction, and its own negative direction by this is where XB is decreasing. So it captures the vector relations, so to speak, um, for the accelerations in this system. So it is better to just stick with it and work with it all through. Okay, so we have these relations. We're going to keep them for now and say this is equation Roman figure 1. This is another equation, say Roman figure 2. And by that, we will proceed to say what we have next to do is the kinetics, because in this case we're interested in some force P. So the kinetic analysis will require us to find some force P, not acceleration. So we should get the acceleration here because we have enough details to do that. So We can get the acceleration of this 40 kilogram body because that's what this refers to, and that will be acceleration of A, and by that we can get the corresponding accelerations of B and C, which expectedly will be equal in magnitude, okay, consistent with our observation that they will have the same acceleration magnitude actually. So let's get right into it now. So we know that for body A, we have been provided some kinematic details from which you can get its acceleration. So let us quickly do that. Okay, so we now say that but for body A, what do we have? So let us now we have given ourselves some restriction. We have by this analysis said or um, given ourselves this restriction that the positive coordinate direction for A is downward. So we're going to stick with this coordinate axis that we have so defined for the motion of A. So we know it is positive downward. So we're going to have its own motion analyzed now. And for our coordinate system, we will stick with what we have up there. We know it is positive downward. So let us say that its initial position is here. So this is x, okay? This is what defines the motion of A. Positive downward is the coordinate system we will use, okay? So this is to tell you or stress the point of that fact once again that once you have done this, you have given yourself a restriction and you must keep with it all through the analysis. So that is precisely what we are doing here. And for that, we say that this initial velocity we're told is 3.5 meters per second up. So if it is up, since positive is down, if it is up, that means that is negative. So we have V naught equals V naught equals 3.5 meters per second. And we are told that the velocity reaches 6 meters per second in 10 seconds. So that means the final velocity upward speed of 6 meters per second in 10 seconds. So if it goes upward, that is still negative. So that will be minus. So B, the final velocity, sorry, initial velocity is negative because it's upward. Downward direction is positive for body A, as we have noted up there. So this is going to be minus 6 as well because it is upward, and downward direction is positive. And then we're told that the time during which this occurs is 10 seconds. So we want to get the acceleration. So we're going to make use of the equations of uniformly accelerated motion here. And why is that correct? Because nothing in this problem statement says that anything changes. For instance, maybe the forces in the system or this force is going to change with time or any such thing. So we will assume uniformly accelerated motion. That is, we will assume that the forces in the system will be constant. That is, this is going to be some constant force P that gives this that acceleration within 10 seconds. Okay, so that is the default assumption we will adopt unless otherwise expressly stated or suggested in the problem statement. That is whether the forces in the system change with time or they change with position of the bodies or they change with velocity of the bodies or they change with some other parameter in the system. Okay, so for this case, then we can say that for our uniformly accelerated motion, what relationship do we have between these four parameters? Obviously, that is V equals V naught plus AT. And by that, what is V? The final velocity minus 6 equals initial velocity minus 3.5, okay, plus AT. A is unknown, T is 10. And by this, we can see that the acceleration will be equal to, this is minus 6. Then we'll move this to the other side, that becomes plus 3.5. And then when we divide by 10, we'll get our acceleration, okay, for the body. So acceleration will be equal to, so let us calculate that. Let's bring up our calculator to deal with that. So this is going to give us what is that here? This is minus 6 plus 3.5 minus 6 plus 3.5 divided by 10, and that gives us minus 0.25. So we have this to be minus 0.25 minus 0.25. Of course, that will be in meters per second squared, consistent with the unit in this system. So we have the acceleration of A to be minus 0.25. Minus implies that the acceleration is directed up, okay, because positive for A, based on what we have defined here, is down. So by that, we can now obtain so that is to say, the acceleration of body A equals minus 0.25 meters per second squared based on the coordinate system we have established above. And so why did we have to stick with that coordinate system? If we didn't stick with the coordinate system, if we took this to be positive upward, for instance, we would obtain a positive acceleration here. And if we brought that into this set of equations, we will get completely wrong answers as to the signs of these accelerations. So that is the problem we have avoided completely by just sticking with the coordinate system we have so defined. Okay, and so making use of equation 1 now, we can make substitutions so that we obtain the acceleration of B, and then equation 2 to obtain the acceleration of C. So using equation Roman figure 1, we know acceleration of A will be equal to acceleration of A plus acceleration of B is equal to 0. So we can have that to be minus 0.25 plus acceleration of B equals 0. So by that, we see that acceleration of B will be equal to 0.25. So that will be in meters per second squared. So we take note of that. And if we make use of equation Roman figure 2, we will see that acceleration of C will be equal to this. So we'll put all of those together. Negative of acceleration of B, so that's minus 0.25 plus acceleration of C will be equal to 0. And from this, we have acceleration of C to be equal to plus 0.25 meters per second squared. Yes, so with that, we are good to go. So we know that, as expected, the accelerations have the same magnitude. This being negative is because the body A will be moving upward under this condition, and we are taking a positive direction as downwards, okay, according to the restriction provided by this coordinate system we have used for A. So the others will be positive, meaning it will be in the direction of increasing xb. Yes, this will be moving this way. This will also be moving this way. Positive because that is in the direction of increasing xc. So that is consistent with what we have always done. Okay, so we will now keep this result and get into the kinetics of the problem so that we will now finally obtain the value of the force P. So that should be quite easy now. What do? We draw the free body diagrams for each of the bodies in the system. So I will start with body A, draw its free body diagram. Of course, we know there are two different cables here, so there will be and we've been told that the the pulleys are frictionless, so the tension on both sides of the pulleys will be the same. Okay, and so for this also yeah, on both sides of the pulley will be the same, and the same will happen to this. So the tension here in this cable, say T1, is the same thing as the tension in the other portion of the same cable, T1 here and T1 here. So for this we'll call it T2 because it's a different cable. Okay, we call it this T2. The tension here is T2 and the tension here is T2 as well because there is no friction here in the pulley. Okay, and of course, if that was not stated clearly in the problem statement, we will adopt that as an assumption and also state that in our solution. Okay, so let's go right into this now. So we know that for body A, we will have something like this for body A. Okay, the weight, this is vertical, so the weight of the body will be acting downwards. So I'm going to put that here. You can guess why I'm putting that here, because the body A will have some tension right here. So the tension, of course, tension is always directed away from the body in consideration. Okay, so it doesn't matter if we put this as T plus WA up there, it won't make any difference. So we just want to avoid that issue. Then we see also that body A is in contact with this vertical surface. So because of that, we know there's going to be some normal reaction from that surface. So we can include that here as well. That is the normal reaction on body A. So we can call that R on A. And that is body A. Then we say this, those are all the forces acting on body A, of course. So we know that. So you might be wondering, how about the frictional force? Because there's frictional force in this system. Yes, you can include it. But okay, we get to see it now. As we will find out, that frictional force will be zero. Okay, but of course, we know that we should get the actual direction of the frictional force. Okay, so if the body is, we know the body is actually moving up. So if it is moving up at under the instance considered here, or for the interval in consideration here, the frictional force will be directed downward. Okay, so we know the frictional force will be directed downward, so we can indicate that here and say that is the frictional force on body A. So we can call that F sub A. So this will be equated to the kinematic, or say the kinetic diagram for body A. That is the mass of A multiplying the acceleration of A. So that is going to be directed downwards. M-A-A-A. So you might be wondering, why are we directing this downward? Don't we already know that the body is moving upward? We know, but we will not use that. We will assume the direction already provided by the axis, about by the kinetic or kinematic analysis we have done here. We have restricted ourselves to this axis, so we will always adopt the positive direction for that axis. Of course, we know in this case acceleration of A is minus 0.25. So when we get there, we will use minus 0.25. Okay. Once we do that, then it takes care of whatever the actual direction is meant to be for us. So we will stick with this coordinate system all through, okay, to avoid confusion. And that is that for body A. Then for body B, we know it rests on that horizontal surface, so its own normal reaction will be directed upward. There will be tension T1 right here. There'll be another tension T2 because this is a different cable entirely. And then the weight of the body vertically down. The frictional force, because this actually moves to the left, the frictional force will be to the right. So let us indicate that here as we draw the free body diagram for body B. So this is body B, its weight acts downward, so we can call that WB. And then the normal reaction on this surface, okay, so we can call that RB, normal reaction on B. And then there is the tension in the first cable away from the body, of course, that will be T1. Okay, so this is T1 as well, okay. So that's differentiate between the tension and the two cables. And then there is a connection to the other cable here. We can call that tension T2. And is that all? There is friction between the surfaces in contact. So since this body moves to the left, the frictional force on it will be directed to the right. So we can call that the frictional force on B. So we call that F sub B. And of course, that will be all for the body B, and that should be equal to the mass of body B multiplying its acceleration. That is the kinetic diagram, okay, for body B. So this is body B again. We know its positive coordinate direction is to the left by what we have used up there, so we direct this to the left as well. So this is the mass of B multiplying the acceleration of B. And lastly, we have the body C, which is not vertical, it is on an incline, which is at 45 degrees to the horizontal. So we're going to make use of that fact here as well. So the normal reaction here, it has to be normal to this surface. So it's going to be directed perpendicular to this incline. And we have the weight, which is vertically down. We have the frictional forces. This moves down, the frictional force will be up the incline. So we can put all of those together. And also the force P as expected. So we have 45-degree angle here. Then we include the block C. Then we have normal reaction from this surface, which will be perpendicular to this surface. So we're calling that normal reaction R on C. Then this moves down the incline, so the frictional force on this will be up the incline. So we can have that as the frictional force on C. Then we have the weight of this body. So the weight of this body will be vertically down. So we're going to have something like this. So let's extend this vertically down. All right, so we have the weight of this body. So that is the weight of body C. Yep. And then we have the tension. Okay, tension will directed away from the body. So this is the tension T2. Then the force P, which we are actually looking for. Okay, will be directed as given in the problem statement downwards. Okay, so with that, we are good to go for body C. We have indicated all of the forces. There is friction directed upward because the body moves downward actually. So that is directed upward as indicated, and then force P as indicated also directed down the incline, and this is directed up the incline. That is tension T2 because that's the tension in the second cable. Okay, the normal reaction will be perpendicular to the surface of contact, and the weight will be acting vertically down. So with that, we have the free body diagram for body C here. So we say this is equivalent to or equal to the kinetic diagram for body C. Of course, we should maintain the orientation, please. So this is going to be equal to, this is also going to be positioned, okay, along the incline. And of course, for this, we know its positive direction for its coordinates is down, so that is going to be equal to the mass of C multiplying the acceleration of C. So this is body C, this is body C. Okay, so that's all we have here. Of course, let us indicate this angle. This angle is 45 degrees, and of course, you know this is perpendicular to this. So whatever this angle makes with the horizontal, it will be what this one makes with the vertical. So this is going to be 45 degrees. Okay. So with that, we are good to go for our diagrams. So we can now attend to each of them. So think about what we want, what we need to get for a moment. We need to get the first P. That is the reason we're doing all of this. So how do we get the first P? If we consider this third diagram, I mean that's where we have P. We know that before we can get P here, we need to know the value of T2. Okay, we need to know the frictional force. Of course, we can get the frictional force from the normal reaction, and of course, we know the coefficient of friction in the system, which is 0.1 as provided in problem statement. So before we can get P here, we know we need T2. And for us to get T2, we will need T1. For us to get T1, we will need this diagram. So that tells us that we cannot escape having to analyze all of the diagrams as provided here. So we start with the first one, analyze it completely, and obtain T1 from it. And with that, we come to the second one, obtain T2. And when we have T2, we come to the third one and obtain the value of P. And that will be all for this problem. Okay, so let's get right into it. So we now say that considering the body A, so for the body A, let us take the summation of forces. We can start with the x direction, okay, taking the right word as positive and equate that to mass multiplying the acceleration of the body in the x direction. So we want to start with the direction where we have the normal reaction because that will be faster. Once we have the normal reaction defined, we know clearly what the frictional force will be. So when we're taking the other direction, we know what we're substituting for the frictional force already. So we don't have to wait to do the other one first. Okay. So when you look at the forces in the x direction here, only RA is in the x direction and it's directed to the right. So that is plus RA. There is no other force that is directed to the along the horizontal or has any components in the horizontal direction. So that will be plus RA. So we will have for this plus RA, and that will be equal to acceleration in the x direction. We know the acceleration of this body, the only acceleration it has is in the y direction, so that is perpendicular to the x direction. So there's no acceleration in the x direction, so then RA equals 0. So that is that about that. Since we know that the frictional force is equal to mu multiplying the normal reaction, and by this we know mu is as given in the problem statement 0.10. We have now found Ra to be 0. Then quite obviously the frictional force there is 0. So quite easy. I told you earlier that even if you didn't include that, you'll be fine. The reason is before there will be frictional force, there should be a normal reaction. And before you can have a normal reaction, reaction means it is due to some action. So if there is no action of some force trying to press this body against that vertical wall, okay, let's go into the actual, let's look at the actual diagram for you to have a feel of that. If there is no force that tries to press this body against this wall, then there can't be any reaction from the wall. Reaction simply means it is a response to some action. So there is no action, then there is no reaction. Or action and reaction are equal and opposite. So for this situation, there has to be some action. In this case, what is the action that presses this body against this surface? It is the weight. So the weight, that's the force of attraction between this body and the center of the earth, presses this body against this surface. So there's going to be some normal reaction provided by the weight in this case, because there's no other force that tries to press it or separate it from this surface. Okay, and in this case, there is also the weight, but the weight is not directly perpendicular to the surface. So we'll get some components, all of the components of forces that is perpendicular to the surface. That is what directly presses this body against this surface, and that is what will determine what the normal reaction from this surface will be. Okay, so when there is no such thing pressing this against this, it's like you just have two bodies that are in contact and then they're moving relative to each other, but then there's nothing that presses them against each other. So it's still good. There is no friction in that case at all. Okay, so that is the idea, and we've confirmed that for ourselves now analytically, so we can move on. So we now consider the for the same body, the summation of forces in the y direction taking upward as positive. Of course, I've mentioned that repeatedly that when you're taking this Newton's second law equation, you can adopt any direction as positive direction. It makes absolutely no difference to our overall result. Just ensure that you stick with whatever you have told yourself is the positive direction. Okay. So for this summation of forces in the y direction of body A, those will be T1 plus, because it's upward as we have defined for ourselves now, and then WA is downward, so T1 minus WA minus FA. Of course, we know this is 0. Okay, we're going to insert that. And then we see MAA is downward, so that will be negative of MAAA, because we are taking upward as positive in this equation. So we're going to have for this situation T1 minus the weight of A minus the frictional force on A, because those are directed downward, is equal to the mass of A negative of the mass of A multiplying the acceleration of A. Yes, we're good, right? Because this is downward, so upward is positive, okay? Upward is positive, that's a T1, all of the others are negative, okay? Because they are downward, right? So by this, we can substitute all of the values we already know. So we're looking for T1. We know WA because we know the mass of A, that is, the 40 kilogram body. So the mass of A is 40 kilograms. So by that, we can proceed to say this is the weight of A then will be equal to 40 multiplying G, which is 9.81, and then minus FA. We just obtain FA of that to be 0. You should see why now it is just beneficial to just take the summation of forces along where we have the normal reaction first, okay? And then this will be equal to negative. What is MA? 40 as we have it. And then what is AA? We found that already in this case. We found it to be negative minus 0.25. So we're going to use that as it is. Minus 0.25. So this is going to be equal to minus 0.25. And by that, we know what our T1 should be. T1 will be equal to, so we can take this to the other side. Okay, that will give us 40 into 9.81. Okay, then minus minus, these minuses will become plus. Another 40 into 0.25. Of course, 0 is forgotten, so it has no influence on this. So from this, we can clearly see that we have our T1 already. So T1, if you like, you can say is equal to 40 into 9.81 plus 0.25. And that gives us, let us consult our calculator here. We have this to be 40 multiplying 9.81 plus 0.25, close the bracket, and that is equal to 402.4. So we take note of that as 402.4, and that is in newtons. Okay, so with that, we're good. We're done with the diagram for body A. So let us move on to the diagram for body B. Of course, as we noted earlier, that will help us obtain the force T2. So we say for body B, for body B, what do we have for body B? So this is for summation of forces, we should go in the direction that has the normal reaction first, so that we will use that to get a frictional force when we get there. If this didn't have the frictional force, of course, we wouldn't even bother about this. We just go with this direction directly. Okay. So for this, we have for that direction, that is the y direction. So let us take summation of forces in the y direction first. Of course, taking the upward direction as positive. We equate this to mass of the body multiplying its acceleration in the y direction. And for that, we have what do we have there? RB positive, WB negative. So that's all we have there. So that would be RB, the reaction on body B, was positive minus the weight on B, and that is equal to 0. Why? Because the acceleration of B is in the horizontal direction, so it has no component in the vertical direction. And by this, we know that the RB is equal to the weight of B. Okay, so with that, we are good to go. And by that, we can get the frictional force on B. We know frictional force will be equal to coefficient of friction multiplying the normal reaction. So by this, we know this will be 0.1 multiplying the normal reaction, which is the weight of B. And of course, we can calculate this now as 0.1 multiplying the weight of B, that is mass of B multiplying acceleration due to gravity, which is 9.81. The mass of B as given in the problem statement is 15 kilograms. So we will just insert that here. So that is going to be 0.1 multiplying 15, then multiplying 9.81. So we can just obtain this and write it out before we proceed. So this is going to be 0.1 multiplying 15, then multiplying 9.81. So that gives us 0.1 multiplying 15 multiplying 9.81. Yes, 14.715. So the frictional force there is 14.715. So that is the frictional force on body B. Obviously not zero. So we keep that. Then we take the summation of forces on the same body in the other direction. So that is the x direction. We're taking the rightward as positive. That should be equal to the mass of A, so the mass of the body multiplying its acceleration in the x direction. So let's get back to body B and take the summation of forces in the x direction. That is T1 to the right, FB to the right. So T1 plus FB, then minus T2. Okay. Then this is going to be equal to minus MBAB because that is to the left. And we're taking rightward as positive. So for that, we have plus T1 plus FB, then minus T2 equals minus M of body B multiplying the acceleration of body B. So into this, we can insert all of those forces that we already know. Okay, from here we know T1 is 402.4. We know FB is 14.715, so we can insert that here. This is 402.4. We have 402.4, then plus 402.4, yep, then plus FB, which is 14.715, then minus T2 equals minus MB, the mass of B, as we have it up there. Of course, we used it here just now. That is 15. Acceleration of B, we got it already, so we're just going to insert it exactly as we obtained it here, which was positive 0.25. So this is going to be positive 0.25. So this is 0.25. We close that off. And from here, we know we can obtain T2 already. So this is us T2 equals, we can move T2 to the other side. For instance, this is going to give us 402.4, then plus 14.715. Okay. We'll move this to the side and I move this here. This will be plus 15 into 0.25. And by that, we can obtain T2 already with our calculator. So let's bring up our calculator right again. We have 402.4 plus 14.715. 402.4 plus 14.715 plus 15, okay, multiplying 0.25. So that gives us 420.865. 420.865. 420 0.8, 6, and 5. And that is obviously in newtons. Okay, so with this, we're done with the body B. We now consider the body C. Okay, for the same analysis. So what do? Go in the direction of the normal reaction first so that we'll obtain that, and we obtain from that the frictional force, so that by the time we're dealing with this, we already know the frictional force. So let us say for body C, we're dealing with these directions. Along the incline, we're taking this as the x direction and this as the y direction for body C. So we'll do the same thing now for body C. So we say that for body C, what do we have for body C? Summation of forces, according to what we have there in the y direction, taking up perpendicular to the incline as positive, should be equal to mass multiplying acceleration in the same direction. And by that, let's get back to it. We have this reaction force, which is in the positive direction, but taking the upward as positive. So this is positive direction. We can extend this way so that we clearly see that WC, the weight of C, will have some component here because this angle will also be vertically opposite that, which is 45 degrees. So the component of WC here will be WC cos 45 degrees. And that will be down, okay, perpendicular to the incline. So altogether we have RC minus WC cos 45 degrees, and that will be all. All of the others are perpendicular completely to this normal. Okay, so we have RC minus WC cos 45 degrees, and that will be equal to 0 because the body does not move in that perpendicular direction, or it has no acceleration in that perpendicular direction. So this will be equal to 0. And from that, we know that the reaction on body C is WC, okay, multiplying the cosine of 45 degrees. And by this, we can get the frictional force on body C. So we can say that the frictional force on body C, we know that should be equal to, okay, let's not jump the process, mu multiplying the normal reaction on C. We know mu as provided in the problem statement is 0.10. Then we know RC is WC multiplying cos 45 degrees. And by that, we know this is 0.10 into WC, the weight of body C. We know that for body C, the mass as provided in problem statement is 10 kilograms. So this is going to be 10 kilograms. So we have this to be the mass of C, which is 10 kilograms, multiplying the acceleration due to gravity, that is 9.81, and then we have this multiplying cos 45 degrees. Okay, so our calculator can just give us what that is. So we get for this the frictional force on body C to be equal to, let's consult our calculator, 0.1 times 10, that is 1. Okay, so altogether we just have 9.81, and then multiplying cos 45 degrees cos 45. So our calculator is in degrees, we go, so this is cos 45, and then we have 6.936717523. Okay, so I'm just going to leave that as 9.81 cos 45. Okay, so avoid approximation errors. 9.81 cos 45 degrees. Okay, so let me leave that because 0.1 times 10 is 1. Okay, so of course this will be in newtons. So let's move on because it's a by the way result. And now we're good to go for body C. We can now take the summation of forces in the x direction, that is along the incline for this case. And when we do that, what do we get? Summation of forces in the x direction, okay, taking up the incline as positive, should be equal to mass multiplying acceleration in the x direction. So what do we have there? Let's see, that is T2. So we have T2 up, then P is down, so that is negative. RC is perpendicular, so there's no component there, but WC is not perpendicular to the surface. So it's going to have a component, obviously, if we extended this way, and then we projected this parallel to that inclined surface, this will be perpendicular to this, and so the component of this perpendicular to parallel to the inclined surface will be along this direction, and that will be given by WC sine 45 degrees. This one here will be sine 45. This is cos 45 degrees. Okay, So with that, we know there is going to be the component of the weight which acts down the incline, which is given by WC sine 45 degrees. That will be negative WC sine 45 degrees. Then minus P, then plus T2, then plus FC. So with all of those, we are good to go. We can say that we have T2 plus FC, T2, then plus FC, then minus WC sine 45 degrees, then minus P should be equal to the mass of the body multiplying its acceleration, okay, in that direction. So that is negative as well because it's down the incline. So we have minus mc AC. So for this we have minus mc AC. This is equal to minus the mass of C multiplying the acceleration of C. So going forward, T2, do we know that already? Yes. FC, do we know it already? Yes. WC, do we know it already? Yes. MC, yes. AC, yes. The only thing we don't know yet is P, which is what we're looking for. So we can just make it the subject of the formula first. So this is going to be equal to P, moving that to the other side, and then moving this to the other side as well. We're going to have this to be T2 plus FC minus WC sine 45 degrees, so sine 45 degrees, and then we have that is going to be plus the mass of C multiplying the acceleration of C. Okay, so with this we can make substitutions. What is T2? We add it up there and we add it to be 420.865. So this is 420.865, then plus the frictional force on C, we add it up there to be 9.81 cos 45 degrees. Okay, so that's it here. 9.81 cos 45 degrees. Then we know minus WC. The weight of C, we know the mass up there is 10 kilogram. So the weight is going to be 9.10 multiplying 9.81. Then multiplying sine of 45 degrees. Then we have that to be, so this is it here. Then we have plus mass of C still 10, acceleration of C, we insert it precisely as we obtained it here, okay, with its sign. So it's positive 0.25. So that is going to be positive 0.25. And with this, we are good to go. So our calculator will tell us now what the final expression is for the for the first speed. So bringing that up, we have 420.865. Then we have plus 9.81 cos 45 degrees cos 45 degrees. Then negative of 10 multiplying 9.81. So we can say that is 98.1. 10 multiplying 98.1 and 9.81 is 98.1. Then multiplying sine of 45 degrees, we close the bracket. Then plus 10 multiplying this, so that is 2.5. That will be plus 2.5. And that gives us 360.9345423. So let us check that we have done the proper thing here. 420.865 plus 9.81 cos 45 degrees minus 98.1 sine 45 degrees plus 2.5. So that gives us 360.93. 360.9345423. But this is our final answer, so we can just write out our final answer of 360.934. Let's say 360.93. Okay, for now. So this is 360.93, and that will be in Newton. Of course, if we're going to write our final answer, we expect that to be in three significant figures. So that is just going to be 361 Newton in three significant figures, and that is that about that. That is our final solution to the problem, and that's all we have to do for this. Okay, so that is the idea. So why I have decided, and I recommend that you stick with the method, is to avoid confusion completely. Just stick with this approach. Deal with this. obtain the relationships this way. It guides you, okay, all through. Yes, you might say, oh, that unnecessarily complicates the issue because it unnecessarily formalizes the whole solution process. Yes, that is how exactly how I want you to approach it. Okay, so I don't want you to use some crude method here, please, to avoid confusion, to avoid running into unnecessary errors. This helps you capture all that needs to be captured. It helps you capture it helps you take care or take note of all that you need to take note of when dealing with problems of this kind. Okay. Again, I'm going to say this. Yes, we know that they are going to have the same acceleration. Yes, we know that you could obtain the acceleration here to be 0.25 and then just assign it to every one of them and go ahead and analyze the motion with this. Yes, that works perfectly. It should give you the same result if you did that correctly. And if you were going to do that, that means you would not have to write out all of these equations any longer. You just observe that, okay, since the bodies will move together, they will have the same acceleration. That is not precisely a correct statement, but we will have the same magnitude of acceleration will be a better thing to say. And because you know this moves upward, yes, then definitely this moves leftward and then this moves down the incline, yes. And then you know the actual direction of the forces in the system, you know the actual direction of the frictional forces. So if you approached it that way, without having to go through all of this, which is perfectly okay if you did that because of the simplicity of the connection here, then, when drawing these kinetic diagrams, you would already know the actual direction here, and then you will use the actual direction directly so that you will use positive values of acceleration all through. So if you did that, that will be perfectly fine. You would obtain the same result. You can give it a try. Okay, but I want you to always approach it this way. It shows that you have a proper understanding of the analysis we're doing here. So it's good that you always analyze like this because you might have something that is more complicated. So you don't assume that the accelerations will have the same magnitude. Just analyze it first, okay, and see that for yourself. Okay, so that's all for the solution to this problem. I'll see you in the next lesson as you consider yet another example on the concept of this chapter. Thank you for watching.